Spin wave. A spin wave is a propagating disturbance in the ordering of a magnetic material. These low-lying collective excitations occur in magnetic lattices with continuous symmetry. From the equivalent quasiparticle point of view, spin waves are known as magnons, which are bosonic modes of the spin lattice that correspond roughly to the phonon excitations of the nuclear lattice. As temperature is increased, the thermal excitation of spin waves reduces a ferromagnet's spontaneous magnetization. The energies of spin waves are typically only MeV in keeping with typical Curie points at room temperature and below. Theory. Experimental observation. Spin waves are observed through 4 experimental methods: inelastic neutron scattering, inelastic light scattering, Brillouin scattering, Raman scattering, and inelastic X-ray scattering, inelastic electron scattering, spin-resolved electron energy loss spectroscopy, and spin wave resonance ferromagnetic resonance. In the first method, the energy loss of a beam of neutrons that excite a magnon is measured, typically as a function of scattering vector or equivalently momentum transfer, temperature, and external magnetic field. Inelastic neutron scattering measurements can determine the dispersion curve for magnons just as they can for phonons. Important inelastic neutron scattering facilities are present at the ICES neutron source in Oxfordshire, UK, the Institut La Langevin in Grenoble, France, the high-flux isotope reactor at Oak Ridge National Laboratory in Tennessee, USA, and at the National Institute of Standards and Technology in Maryland, USA. Brillouin scattering similarly measures the energy loss of photons, usually at a convenient visible wavelength reflected from or transmitted through a magnetic material. Brillouin spectroscopy is similar to the more widely known Raman scattering, but probes a lower energy and has a superior energy resolution in order to be able to detect the MeV energy of magnons. Ferromagnetic or antiferromagnetic resonance instead measures the absorption of microwaves incident on a magnetic material by spin waves, typically as a function of angle, temperature, and applied field. Ferromagnetic resonance is a convenient laboratory method. One group at the Max Planck Institute of Microstructure Physics in Halle, Germany proved that by using spin-polarized electron energy loss spectroscopy SPELS, very high-energy surface magnons can be excited. This technique allows one to probe the dispersion of magnons in the ultrathin ferromagnetic films. The first experiment was performed for a 5 ml Phi film. With momentum resolution, the magnon dispersion was explored for an 8 ml SCC Co film on Quone and an 8 ml HCP Co on 110, respectively. The maximum magnon energy at the border of the surface Brillouin zone was 240 MeV. Practical significance. When magnetoelectronic devices are operated at high frequencies, the generation of spin waves can be an important energy loss mechanism. Spin wave generation limits the line widths, and therefore the quality factors Q of ferrite components used in microwave devices. The reciprocal of the lowest frequency of the characteristic spin waves of a magnetic material gives a time scale for the switching of a device based on that material.